Good afternoon to all. Let us discuss today's topic, that is current chopping. We know when our circuit breaker is open, circuit breaker contacts are open, arc is struck between the circuit breaker contacts. So this arc is nothing but the ionized particles, okay, that are struck between the circuit breaker contacts. And we already know, as shown in this image, the circuit breaker contacts are placed in a dielectric medium, that is a deionizing medium. Okay, so whenever circuit breaker contacts are open and when arc is struck between the contacts, if the dielectric strength is very high, that is deionizing medium is the strength of the deionizing medium is very high, or deionizing force is very high, then arc can be easily interrupted. Now, as we have already discussed, the arc must be interrupted at natural current zero if this waveform which is shown here, current waveform, is the arc current. It is similar to your arc current waveform. At the instant of natural current zero, arc must be interrupted. Okay. So when our circuit breaker is interrupting low magnetizing currents, okay, it is observed that the deionizing force will be such a high value that before even the current arc current loop reaches to the natural current zero, it is interrupted in between before reaching the natural current zero. Okay, so actually in general, deionization should occur at natural current zero, but deionization occurs at is occurring due to the high dielectric strength between the contacts at some other instant instead of natural current zero. So the deionization at any other stage of the arc is disadvantageous and unnecessary. Okay, if deionizing force is applied in the middle of the current loop, if this is the current loop, let us consider this loop. If the deionizing force is in between the in between in the middle of the current loop, more voltage will be required to maintain the arc current. Okay, more voltage will be required. We know the potential, because the potential, if there is sufficient potential gradient between the circuit breaker contacts, then arc will be maintained. If sufficient potential gradient is not maintained between the circuit breaker contacts, arc cannot persist, it will extinguish. Okay, so if the deionizing force is applied in the middle of the current loop, okay, instead of natural current zero, more voltage is to be required to maintain the arc current, and it will cause release of energy which is required to be disposed of. Okay, this is one of the drawback. Okay, so if the deionizing force, if the dielectric strength is very high, okay, in between the circuit breaker contacts, okay, and if the arc is interrupted in between the loop instead of natural current zero, then lot of energy is released. That energy is to be disposed. Okay, that is one of the drawback if the arc is interrupted in between the loop. Another drawback is it will causes current chopping. Okay, it will cause current chopping, hence phenomena of current interruption before natural current zero is reached. Okay, so let us discuss in detail about this current chopping. So whenever the circuit breaker has to interrupt low inductive currents such as magnetizing currents of transformer or a shunt reactor, the rapid deionization of the contact space and blast effect may cause the current to be interrupted before its natural zero. So in practice, it is observed that while interrupting the magnetizing currents, which is a low inductive current, okay, So whenever we are interrupting low inductive currents of the transformer, unloaded transformer or shunt reactor, okay, rapid deionization will occur in between the contacts. Hence, arc will be interrupted before it reaches to the natural current zero. Okay, so whenever arc is interrupted before the arc current reaches to natural current zero, that is known as current chopping. Okay, the necessity of interrupting small inductive currents arises whenever we are disconnecting an unloaded transformer. Okay, so let us assume that an unloaded transformer is connected to the system. Okay, so this is the winding of the transformer. This is an equivalent circuit. This is an equivalent circuit of the system in which this is an equivalent circuit of the system in which to which the unloaded transformer is connected. Let us assume this is the winding of the unloaded transformer, and you want to disconnect this unloaded transformer from the supply. Okay, and in order to disconnect the transformer, we are using a circuit breaker here. Okay, so the purpose of the circuit breaker is it has to operate as a switch to disconnect this unloaded transformer from the supply. So when it is about to open, means it has to interrupt the low magnetizing current that is in the windings of this no load transformer. So the current is smaller than the winding current of the transformer, which is the low inductive current. Okay, is very small when compared to the normal current rating of the circuit breaker. Okay, the circuit breaker has to interrupt low inductive current of the unloaded transformer. So that low inductive current is very small when compared to the rating of the circuit breaker. So the available deionizing force within the circuit breaker is sufficient enough to force the arc when the circuit breaker is opening. Okay, and when arc is struck between the circuit breaker contacts, the available deionizing force will be sufficient to force the arc from its high value straight to zero before the arc current actually reaches to the natural zero point. Okay, so current chopping is a serious drawback as it produces high voltage transient across the contacts of the circuit breaker. So if you see here, just for example, I have considered an onion here. So onion, this shape of the onion is similar to the loop of the current waveform. Okay, if you can see, you can observe here, a person is chopping this onion. Okay, so whenever the circuit breaker has to interrupt low inductive currents. Okay, since the low inductive current, the magnitude of that inductive current is very small when compared to the rating of the circuit breaker, the available deionizing force will be sufficient to interrupt the current, okay, straight away from its high value to zero. Okay, so if this is the loop, you can say a person is chopping here, is cutting here. So the current from this peak, as he chops from top to bottom, okay, from top to bottom, the current is suddenly going to zero at this particular instant where the person is chopping. Okay, so suddenly instead of this edge, let us say this is the current zero edge of this loop of current. Okay, instead of interrupting current at this current zero point, it is being interrupted at somewhere within the loop. Okay, for example, a person is chopping here, so let us assume the current has been suddenly falling down from its maximum value to zero here. Okay, so whenever current is suddenly brought to zero, okay, straight away from its high value to zero, instead of naturally decreasing and going to zero, uh, current chopping problem occurs. Okay, so which is a serious drawback, and because of this, high voltage transients will appear across the contacts of the circuit breaker. Okay, So you can see here, this is the waveform. Okay, so let us assume this is our arc current. Okay, this is the arc current, which is naturally, it seems as if as I move from my left side to right, it seems as if it is naturally going to its natural 0 point. Okay, it is moving towards its natural 0 point. Okay, it seems as if. Okay, so whenever the circuit breaker has to interrupt the low magnetizing currents, suddenly at this instant, you can observe the cursor, suddenly the current becomes zero. The current is becoming zero at this particular instant. So I tried to expand the screen, but my system is not responding. That's why I have to end the show here. So, okay, yeah, now it is varying. So suddenly current becomes zero. Okay, so this suddenly the current reaching to its zero value is because of the large deionizing force. Okay, which causes the current to collapse to zero immediately. Okay, current chopping occurs. This is known as current chopping. Okay, so immediately when arc current becomes zero, actually, this arc current was flowing from the source through the inductance and the circuit breaker contacts. So the energy contained in the inductor is in the form of energy stored in the inductor is in the form of electromagnetic field. It cannot immediately become zero. Okay, the electromagnetic field energy which was stored in the inductor, it cannot immediately become zero. Okay, it cannot immediately become zero if it has to be changed into some other form of energy. Okay, so the energy, the electromagnetic energy stored in the inductor, okay, if you can see here, the energy which is stored in the inductor, it cannot immediately become zero. It has to be converted into some other form of energy. The only possibility here in this is the conversion from electromagnetic energy to electrostatic energy is possible. Electrostatic energy is possible here. Otherwise, there is no other possibility. Means the energy that is stored in the inductor will be discharged into the stray capacitance. Okay, so the capacitance is charged with the prospective voltage now. Okay, this prospective voltage will appear across the circuit breaker contacts. Okay, the voltage that is appearing across the circuit breaker contacts as soon as that arc current becomes zero is the prospective voltage. So you can see here, this is the voltage, prospective value of voltage with the chopping. This is the prospective voltage. Now if I is the instantaneous value of arc current, where chops takes place, just for example, small I is the instantaneous value of arc current where chops takes place, the prospective value of voltage V to which the capacitor, stray capacitance C is charged. Okay, so then whatever energy that was stored in the inductor is discharged to the capacitor. So means the energy in the inductor is equal to energy of the capacitor. So half Li square is equal to half CV square. Okay, so V is equal to I root of L by C. So what is V? V is the prospective voltage. So it will be extremely high when compared to the normal system voltage. The prospective voltage which appears across the circuit breaker contacts. So whatever voltage that is appearing, that is impressed across the capacitor, it will appear. it will be impressed across the circuit breaker contacts. Okay, so that will be very, very high. Okay, so because of this prospective voltage, what will happen is arc will restrike. Okay, so when compared to the dielectric strength in between the circuit breaker contacts, this prospective voltage is very high, hence arc will restrike. As the deionizing force is still in action, okay, as the deionizing force in between the circuit breaker contacts is still in action, therefore choke will occur again. Okay, even though arc has restrike, so again you can see the arc current here. Okay, because of the prospective voltage, arc has restrike. You can see the arc current. First restrike, you can see first restrike, this line, second line. Okay, so arc has restruck. Again, what will happen? Because of the deionizing force in between the means dielectric medium between the contacts of the circuit breaker, arc will be interrupted. Okay, arc will be interrupted, and this arc current this time is smaller than the previous value. Okay, it will be smaller than the previous value. Okay, and because the dielectric strength is high in between the contacts, this arc, even though it has appeared, it will once again collapse. Arc current will collapse to zero. As the arc current collapses to zero, the energy from the inductance will be discharged to the capacitor, and prospective voltage will appear across this capacitor, means that same voltage will be impressed across the circuit breaker contacts. So the prospective voltage will restrike the arc. Okay, so the voltage which will appear across the circuit breaker contacts magnitude is given by the second prospective voltage here. Okay, of course the magnitude of the second prospective voltage will be less than the magnitude of the first prospective voltage. Why? Because the arc current during first stroke, first choke, okay, we can say first choke was more than the arc current during second. Okay, okay, now now again due to this prospective voltage, what will happen? Arc will appear across the circuit breaker contacts. Means arc current, again arc current will be there. Okay, you can see the third time. Okay, arc current has appeared again, and the magnitude of this current will be less than the previous one. Okay, you can observe the because of the dielectric strength of the circuit breaker contacts, again the arc is interrupted. Okay, when the arc is interrupted, the inductor will discharge its energy to the capacitor. The prospective voltage will appear across the capacitor as well as across the circuit breaker contacts is given by the due to the third stroke. Okay, so this is it. Okay, third time again arc will restrike because of this prospective voltage. Okay. So this is the prospective voltage that is appearing across the circuit breaker contacts. Okay. So now again what will happen because of this? Again arc will restrike across the circuit breaker contacts, and this process will repeat because till the current finally is suppressed before its natural zero. Before its natural zero, this is the natural zero point. Before the natural zero itself, current is suppressed. Okay. So after few intervals, we can say. Okay, so these are all the prospective voltages which are gradually reducing as the magnitude of the restriking arc current is reducing. Okay, at last what will happen is after natural current zero, recovery voltages, means normal frequency voltage will appear across the circuit breaker contacts. Okay. So in order to overcome this, usually across the circuit breaker contacts, resistance is connected. Means resistance switching is used to overcome the problem of current choking. So let us discuss next topic. Interruption of capacitive currents. So, so whenever we want to interrupt unloaded long transmission lines, okay, or we want to interrupt means the we want to disconnect, not interrupt. Whenever we want to disconnect unloaded transmission lines from the system or unloaded ungrounded cables or capacitor bands, it is observed that while disconnecting unloaded transmission lines or unloaded ungrounded cables or capacitor bands, they will cause excessive voltage transients across the circuit breakers. Okay, so while disconnecting, voltage transients will appear across the circuit breaker contacts due to the interruption of these capacitive currents occur. These capacitive currents are due to the unloaded long transmission lines or unloaded ungrounded unloaded undergrounded cables or capacitor banks. Okay, so whenever the circuit breaker has to interrupt the capacitive currents, okay, then voltage transients will appear across the circuit breaker contacts. Okay. So while opening the unloaded transmission lines and unloaded ungrounded cables and disconnection of capacitor banks employed in the network to provide reactive power at leading power factor, okay. So now to discuss about this, let us consider a simple circuit. Okay, so in this circuit you can see an unloaded long transmission line is there. So this line, even though it is unloaded, will carry a capacitive current of I on account of the capacitance CL between the phase and the line and the earth. Okay, between the line and the earth. So where the CS is the stray capacitance, CL is the line capacitance. The value of CL will be more than the CS stray capacitance value. Voltage across the capacitor will not change instantaneously. You already know. The current supplied to the capacitor is generally of small order and can interrupt such currents invariably at first current zero itself. Okay, means the circuit breaker can interrupt these currents at first current zero itself. So let us discuss what will happen while interrupting the capacitive currents of these unloaded long transmission lines. Okay, so let us assume that the circuit breaker is open at an instant of t1. Okay, when circuit breaker is open means the line is open at the instant of t1. So the line will be opened when the circuit breaker is open at instant of t1, and when the line current is at that instant, line current is what? 0. This is the line current. I is the line current. This is VB. VB is the voltage of this stray capacitance. Okay, so it can be seen from this figure that at instant t1, when capacitive current I is 0, the transmission line is at maximum negative voltage. Transmission line is at maximum negative voltage at t1. The line is left in a fully charged condition to this negative voltage value. Okay, okay, negative voltage value which is generated by VB. Okay, so after instant t1, the breaker gap is subjected to the difference of the voltage VB and VC. Okay, this is the VB and VC. The difference of the VB and VC will be left over after T1 across the circuit breaker contacts. So after a time interval of half cycle from A, instant A to B, that is half cycle from A to B, that is at T2, the voltage across the breaker will be 2 times to that of VB value, this VB value, okay, twice to that of VB value, that is 2VB max, okay. So within such a short interval of half cycle, the breaker has been subjected to a severe condition with the result that breaker might restrike, okay. So when voltage has doubled, okay, voltage across the capacitor, stray capacitor has doubled, okay, then that voltage, you know, it will appear across the circuit breaker contacts, okay. So there are chances for the restriking of the arc across the circuit breaker contacts, okay. So and the circuit will start to when arc is restruck, okay. If such condition occurs, then the voltage across the circuit breaker may falls almost instantaneously from 2 times maximum value of VB to 0 if the circuit starts to oscillate, okay. And hence high frequency oscillations are set up which build up the voltage to 3 times maximum value of VB. Okay. So when circuit starts to oscillate, the voltage will fall down and the voltage will again build up in the next cycle 3 times to that of your VB value. Okay. So the restrike current IB reaches zero value, which provides an opportunity to interrupt. The line is charged to a voltage of 3 times maximum value of VB to earth after interruption of restriking current IB. Immediately after point C, this C, the voltage across the breaker contact is twice to that of the maximum value of VB, since generated voltage VB itself is positive maximum value. The voltage across the breaker contacts now continues to increase at D. Okay. At D, this reaches to a value of 4 times to maximum value of VB. Okay. So this reaches to a maximum of 4 times to the maximum value of VB. If the breaker restrikes again at this point, the events of B will repeat on an even more formidable scale, as the voltage swing will now be 8 times the maximum VB, and the line may then be left isolated at a potential of 5 times maximum VB to earth. The energy stored in the capacitor to be dissipated during such arcs is quite large, and the interrupter may get damaged in the process after restrike. Hence, the circuit breakers used for capacitor duty should be restrike free, and it should have adequate rating of capacitive current switching. Okay, usually vacuum circuit breakers, SF6 circuit breakers, or air blast circuit breakers are used for interruption of capacitive currents.